Hi, this is Jeff Galak from Data Demystified, and what I'm going to do today is go through a quick demo of this visualization that will help us understand disease test accuracy. So just to give you a quick layout of what this all looks like, there are three inputs that you could put into this visualization. The first is this number right here, the true infection rate. That's how prevalent is the disease in the population. And so for the moment, I'll just say 5%, which is one of the best estimates for what COVID-19's actual disease proliferation is right now. The next we have is the test false positive rate. This is how often does a test come back wrong, such that it says that someone has a disease when in fact they don't. And then the test false negative rate, which is the opposite, which is how often does someone who has the disease come back with a test that says that they don't. And what you get are the outcomes here. This is what are called the false discovery rate or the false omission rate. These are what you care about as a person who opens up a test result. The false discovery rate tells you how often is it the case that the test is wrong when you open it and you see a positive result. And false omission, which is the opposite, tells you that how often is the test wrong such that when you open it and it's a negative result, it's wrong and in fact you do or did have COVID-19. The way that this visualization works is through this graph right here. This is a graph of 1,000 people and it's color-coded in a very particular way. You see green people. These are people who, in fact, are not infected and are told that they're not infected. These are our true negatives. Reds are our true positives. These are people who are infected and are told that they're infected. Yellows, which we don't have any yet, are going to be people who have a false positive. These are the people for whom the test comes back and says that they have the disease when in fact they don't. And then blues will be false negatives. These are the people who actually do have the disease but are told that they don't. And as we change our values up here, we see how this all varies as well. So let's put in the case I have from the main video, which is a 5% false positive rate and a 5% false negative rate. What we see is this visualization changes. We get a bunch of yellows, those are our false positives, and a few false negatives. And what else we see is our false discovery rate goes to 50%. That means that if you get a positive result, you don't know if you're one of these red people who has the disease and are told that you do, or one of these yellow people who don't have the disease, but are also told that you're due. And in this example, it just so happens that the two are the same, and so it's a 50-50 chance whether you actually have the disease or not when you receive a positive result, which is a far cry from that 95% accuracy, which is implied by a 5% false positive rate. We also see that if you get a negative result, you don't know if you're one of these people down here, these blue people, which are people who actually do have the disease, but were told they don't, or one of the very many green people who don't have the disease and told that you weren't. But that's not a big deal because there's so few blue people relative to the green people, the likelihood that the test is wrong in this case for you is only about 0.28%, which is pretty tiny. And so as you change these numbers, what this will do is hopefully give you an intuition about how these tests work and how accurate they really are. So for instance, let's say our true infection rate is really small, like if really few people have the disease, maybe only 1% of people have the disease. Well, in that case, our false discovery rate skyrockets. Why? Because only a few people actually are sick, these red people. But so many people are being told, these yellow people, that they are sick when in fact they're not, that you're much more likely to actually be told that you have the disease when you actually don't. Which means that you're much more likely to actually have a false positive than to actually have the disease. That's a big problem. Giving just one more example, let's take the case of a disease that's really prevalent. Let's say the disease is so prevalent that 40% of people have this disease. Well, in that case, our false positive rate of 5% isn't so bad. Because when we compare the people who actually have the disease, our reds over here, to the false positives, which are our yellows, we see that there's many more people who actually have the disease as compared to the people who are just told that they have the disease but don't actually have it. So our false discovery rate, the likelihood that your positive result is wrong, it's only 7%, which is pretty good. So what we see is that as infection rates increase, as diseases become more prevalent, false positives become less of a problem. In contrast, false negatives start becoming a bigger problem. That's not the case here, but let's look at one more really extreme value. Like let's say that the true infection rate is somewhere like 80%. Most people have the disease. Well, now false negatives or the false discoveries is basically not an issue at all, but false positives become a real problem. Well, why is that? Well, because there's so many blues here now. Those are the people who actually have the disease, but they're told that they don't. There's so many blues compared to the greens, those are the people that actually don't have the disease, that the likelihood that the test is wrong is now about 17%. So as you see, you can play with these values and see if you can get a deeper intuition for the relationship between infection rates, false positive rates, and false negative rates. Again, if you find this information useful, take a moment to like this video and subscribe to the channel.